Welcome everyone to another OCP Tab call. This is call number 133. Today we have Roel from Fugro AtomiChron. So Roel has a Master in Engineering in Business Development from Business Developer. Sorry, is the Business Developer for Fugro AtomiChron Timing Services. Roel has made significant contributions to the field in the 12 years of experience in GNSS time synchronization market, which includes working at Arbiter Systems, primarily within the power and energy sector. Also, he has been active member of the working group responsible for the IEC IEEE 60255-118-1 standard, which is about measurement of synchrophaser for power systems, and has served as the convener for the Cigré working group on time in communication networks, protection, and control applications. Today's talk is about basically the Fugro AtomiChron High Accuracy GNSS augmentation services with updates on the latest. So with no further ado, Roel, the floor is yours.
Thanks, Ahmad, for the introduction, and sorry to make it so long for you when you're not
No
fully...
worries, no worries.
Screen is shared, right?
Yeah.
Everybody can see it. All right, and thanks everybody for joining. So yeah, I presented our service already January 2024. There's some updates over time. I think they're interesting to share to you. I also chose actually this week because last week there was a conference in Mexico where we showed some measurement data that I'll also show here. So let's get started. So yeah, let's go back to early last year when I presented. So our high accuracy service offering. Basically, we stated back then, and that doesn't change. We claim to be within 5 nanoseconds of accurate to UTC 95% of the time. The 5% uncertainty basically is in what UTC will do, which we only find out next month. We also claim less than 1 nanosecond accuracy to the AtomiChron timescale, which is our own built timescale based on hydrogen masers. And we're at least 10 times better than existing high-end GNSS receivers. And we have a very good frequency stability at less than 1 e to the minus 13 at 1,000 seconds ADEF. So these claims have been standing for probably 3 years now since we prototyped this. Not much has changed in that regards. So you might ask what I'm doing here, just watch the presentation of last year. There's new stuff. We now also support UTCk offset data messages. And we've started with an offset message to UTC NIST, as well as UTC PTB, and others are to follow. So for the people that are new here or don't want to watch the entire recording from last year, I'll do a quick update on what the technology is that we use and how we do it. So let's start with reference stations. We as a company have 100 reference stations, so consider the white dots here to be a reference station somewhere in the world that will continuously look at all the GNSS satellites on all the 4 constellations. So again, about 100 reference stations spread across the globe. They have been operational and used for 30 plus years for positioning. So it is something that we've been using for positioning and just applied to timing since about 3 years ago. Again, all the 4 constellations, so not just GPS, not just Galileo, even supporting GLONASS today, although not being used much, but also BIDO, for example. So just to give you an idea of these stations, they are spread around the world. Yeah, there's a big void in Russia for apparent reasons. If you look at this map now, it's an old map, but still it's very valid. There are black stations as well. There are stations that are offline today. But as you can see, it's a very overdetermined system. So whenever a station is offline for whatever reason, There could be antenna failure, there could be a comms failure, whatever. There are plenty of other stations that will cover for that station to get data. So then we also have a ground segment. Basically, we have two control centers, one located in Houston, one located in Singapore. So geographically, they are separated from each other. These national control centers, network control centers, sorry, receive the data from all the reference station, and that's just GNSS observations, so ephemeris, orbits, everything like that. They run fully independent software on both ends, designed by different software engineers. They have uptime of very high of 99.99% of system uptime to serve data to the end user. And I'll get to what data later, no worries on that. So basically, the data we're supplying is PPP correction data. I'll give a bit on PPP after in the next slide, as well as an independent timescale, and now new also UTCk information, but also authentication data. I won't get into detail on that one today. So PPP is actually key to the technology that we use. So PPP stands for precise point position, basically giving you corrected orbit and clocks for every satellite in the sky. So we remove already ionospheric delay, mostly due to frequency in receivers, but we can also now model the tropospheric delays based on the input from the reference stations. So the output from the calculations is SP precise clock corrections and precise orbit corrections. Basically, a GPS satellite will send you its own orbit and clock, and it will update that, but it's not very often. We do that basically in real time, from receiving in a reference station to send it back to a receiver within 30 seconds. So you have much more up-to-date information. You can calculate your position better, but you also have much better time information. On top of that, we also add our own timescale information to make the timescale that you're getting even more stable. PPP is, by the way, used either in post-processing, which BIPM does to actually calculate UTC at the end of every month, and then publish it 10 days later, I think. But you can also do it in real time, and we do it in real time. And just as an idea, the post-process BIPM data isn't very much better than the real-time data that we use. Just a quick asterisk here on SV stands for space vehicles, so basically any satellite for constellations. All right, next, then we have that data from the NCC, and we have to get it back to the end user. We also thought about that, again, for positioning. We've been using this for a while. So again, the white dots here, consider them to be reference station, but then I think orange, I'm a bit colorblind, orange dot would be an end user. So from the NCC through uplink stations, we send data to geostationary satellites. They broadcast that data down back to Earth to receivers. And the receivers, a general GNSS receiver would have an L-band channel to receive this information. It will not need to communicate back. It is a one-way traffic. And you can use the same antenna, so it's very convenient in usage. So we have redundant upload links from the NCC to the geostationary satellites. We have 6 beams, redundant beams, so 2 redundant beams per area, so Americas, Middle East, Africa, and Europe, as well as the Pacific, and covering the entire world with the exception of the North and South Pole. Alternatively, by the way, this data can also be sent over internet through the NTRIP protocol. Okay, so when it gets to the receiver, so basically here on the left, you see our infrastructure and processing. So we feed an AtomiChron timescale. We have our tracking network. We send it over the air, not really a cloud, but still through the clouds. We send the PPP corrections, the AtomiChron timescale, and also the UTCk offset. It lands into the receiver module here. The receiver is receiving GNSS antenna inputs and can also receive external clock input. And then that goes, the GNSS together with the L-band corrections goes into a Fugro software library that's embedded inside the receiver. And our library will spit out orbits and clocks that the receiver can use to determine position and clocks. That is PPP corrected SV data that we feed to the receiver together with our timescale and the UTCk offset. And then the receiver module will basically feed this data out to any equipment it will be embedded in. So yeah, what's new? That's the UTCk offset edition. So the accuracy we already do for a couple of years now. It's going well. People signed up for it. So we're happy with that. But we realized, okay, the reference we had before was against our AtomiChron timescale, which is the commercial company timescale, which people start questioning, okay, that's a commercial timescale. How can we trust it? Is there another way? Can we reference it to something else? Now, we can, of course, not reference to UTC because UTC itself isn't determined in real time. It's only available next month. So we decided to do the next best thing. So we added UTC NIST and UTC PTB offset information to the broadcast. So that enables real-time UTC NIST and UTC PTB at any location in the world within a nanosecond accuracy. Now, a big shout out, don't forget to calibrate because everything will cause delays, including connectors, everything. So you do need to calibrate. And you can either use a golden receiver to calibrate it on site or ship receivers to UTC to NIST or to PTB to have them calibrated there. But this is something you have to think about if you want the accuracy to these UTC realizations at NIST and PTB. So also new is that this is now also integrated in commercial off-the-shelf hardware, as is our high accuracy service, which hasn't been available in other in commercial hardware. Good thing about SparkFun, who took out the task to actually build a GNSS DO based on the technology, is that it's both open firmware as well as open hardware. So I think that fits really well with the community I'm presenting in today. So the Spark PNT GNSS disciplined oscillator by SparkFun is actually just available on their website. You can buy it today. It will probably ship today because they're probably in stock, and it will give you direct access to the technology. So I'll get a bit more on that later. First, why did we choose PTB? Well, PTB turns out to have about the best accuracy to UTC over time. I'm showing you here, and it's in modified Julian dates, so it's still 1,000 days. So almost 3 years of data of the accuracy of PTB reported by the BIPM. There's a link to the database here. You can check it yourself when I send the presentation later. So basically, if you look over about the last 3 years, PTB has never estimated their offset worse than 2 nanoseconds. Well, maybe 2.5 here, but that's still very good to UTC. So using this as a reference will actually guarantee you first that you have a very stable reference and one reference to reference against, but also that you will be within a couple of nanoseconds. Although there's no guarantee, this is historical data, there's no guarantee that the future will look like this, but it's the best guess you can take today. So that's PTB. PTB is in Germany. We do realize there's also US customers, and there's also quite a good US lab, which is NIST, of course. So NIST does perform a little bit worse, to be honest, than PTB, but still not bad. They have been in the last 3 years, they have been within 2.5 nanoseconds of UTC. And that's also a very good performance, of course, that people can reference against and use as a reference, and in the same time traceability to these UTC realizations as well. Okay, a quick overview of how we actually get this data. It is not that we just get it for free. What happens is the following. So a UTCk site, which today is PTB and NIST, will basically provides us contracted PPS and 10 megahertz data, which we feed in the most used receiver in NMI's National Metrology Institutes today for high accuracy timing, which is the Septentrio Polo X5 TR. That GNSS receiver also receives GNSS signals. It sends all these observations to our data centers. In our data center, we in real time process the PPP corrections, which we can also do in real time in a receiver, but in this case, we do it offsite. And then from that, we calculate the UTCk offset, so UTC PTB or NIST, to the AtomiChron timescale. Then we send that information to our uplink stations, to the geostationary satellites, together with the real-time PPP data that we already sent. This ends up at an end-user GNSS DO. That GNSS DO also receives GNSS, and in real time can actually set its BPS output to UTC NIST or to UTC PTB. Now, when I say it, when I show this, it all looks really nice, really easy. It is not, and also a lot of people will not believe me on my blue eyes right away. So next up, I got a couple of performance metrics. So first thing is a bit of a repetition of before on the high accuracy and the stability of the service. What you see here is basically the SparkFun GNSS DO, 10 megahertz output, electrical output measured against the passive hydrogen maser over time, which will give you the stability ADEF shown here, which runs to 1 e to the minus 13 at 1,000 seconds, down to we can actually reach 1 e to the minus 14 and 10,000 seconds. So in the short term, this is totally determined by the oscillator in the GNSS DO, which in this case is a side-time MEMS oscillator, which is quite nice, but if you get a better oscillator, you can push this down in the short term. Now, we're not really in it with our service for the short term, so whatever people want to spend on an oscillator, OCXO, whatever, for short-term stability, just spend as much money and you push this line down to wherever you can push it. But in the long term, we will take over and we will show you, we will make sure that the ADEF goes down like is shown here. And actually, we can even do a bit better. This GNSS DO is still not even optimized for what it can do. There are a couple of modes shown here. You can put the receiver in a rover mode, so basically it'll be able to move around. That gives you a bit worse performance, but would actually allow you to move around with the receiver as well and still get pretty good accuracy. This one is with AtomiChron disabled. They didn't run a test with AtomiChron enabled, but it would look pretty similar to the bottom line here, just a little higher. But you can move around with AtomiChron. It does not matter. It should give you the same accuracy, although we have not driven around with a car on a very good reference clock yet, which we might be doing soon. Then there's static mode, basically position hold mode for other products. So you hold your position and you make sure you stay there and you get a bit better performance. And then with AtomiChron disabled, it looks like this. With AtomiChron enabled, you go all the way down here. So this is actually still not new. We have proven this already 2 years ago with lab-built GNSS DOs. So nothing new here. It's just now you can buy a $2,500 box off the internet and a license from us, of course, and you can get this performance right at home. I got one at home, for example, or in your lab for that matter. Now, on the UTCk, we went a bit step further, I'd say, to get the performance on that. We did a measurement campaign, and this has been published at the IEEE IFCS EFTF conference last week in Mexico. But I'll share this data with you here as well, because I think it's pretty good data. What we did is at PTB in Germany, so the NIST of Germany, we compared PTB against PTB, but the PTB, one PTB coming out of a GNSS DO and the other one being the UTC PTB generated at PTB at a 200-meter baseline. So it's very, very short distance. And the connection between the buildings is a fiber optic link that will give you time over fiber. Fairly simple. So we also went a bit further. We used Deutsche Telekom AG, so DTEC, in Frankfurt, which is about 300 kilometers from Braunschweig, where PTB is. And what we did there is we also put the GNSS DO there and compared it against a local copy of UTC PTB, which they have there, which is established via an L-step fiber link, which is one of the best technologies out there over fiber today to transfer time and frequency. And then the last one we did is we shipped a box to RISE in Sweden, which is the NIST of Sweden or the PTB of Sweden, whatever you want to call it. And we compared UTC PTB from the GNSS DO against UTC SP. It's a 700-kilometer baseline, and we have the option to compare it to two-way satellite time and frequency transfer, which is the technology that NMIs around the world use to compare their own realizations to each other. So these were the 3 locations, and what we did is we measured the local clock again against the transferred UTC PTB clock coming from the GNSS DO, straight from the PPS output, nothing digital. It's an electrical pulse coming out into a time interval counter, and we recorded the time difference output. So we did a 1-month measurement. We actually did longer, but I'll show you data for a month. Also, the second month didn't make any changes, so no worries there. So it's not like we did like a day or an hour or whatever. No, we went for a month to show you everything we did. Now, before we did this campaign, as I mentioned before, calibration is important. So we shipped 3 of these GNSS DOs, well, shipped actually, hand carried them to PTB together with cabling and antennas, so we can calibrate the entire chain to the output of the PPS pulse coming from the box. So we had a really nice day in January. Luckily, there was no snow. It was quite windy and cold on the roof. It was me and a couple of colleagues from PTB. You see the mess which comes with measurements like this. We actually put the GNSS DOs in boxes during operation just to make sure there's no interference, mostly on temperature change. They can stay quite constant this way. Temperature change does influence on this accuracy already the outcomes. And we weren't sure where they were going to end up in Deutsche Telekom and at RISE, how controlled the environment was, and the same with PTB. It is a lab that not a lot of people go in and out, but we weren't sure, so we just for certainty we put them in boxes, and we carried out the calibration. So the calibration was carried out for a week. Basically, what we did is at PTB there are 2 buildings, one of which they actually generate UTC PTB. That's called the Kopferman building. They transfer the 1 PPS and the 10 megahertz, 100 megahertz apparently, to the other building where we did the calibration. So these buildings are 200 meters apart. For this exercise, we actually generated the offset data from the receiver in the left building, and we did the calibration on the right side. So we connected all the 3 GNSS DOs with antennas and cables to a tick, and we calibrated them all against the reference we got from PTB, from UTC PTB. That calibration took about a week, and then we had them calibrated within a nanosecond, easily. Actually, it could have been a day probably. And then what we did is we took one of these GNSS DOs with cable and antenna, and we shipped it to RISE. So the entire chain was calibrated up to the PPS output. We took the other GNSS DO and antenna, and we shipped it to Deutsche Telekom. Unfortunately, they already had a cable installed because it was a long cable, so we couldn't ship the same cable. But we switched out the delays on the cables for the test. And that was Deutsche Telekom, by the way, sorry. And we kept one of the GNSS DOs at PTB just in this configuration and kept measuring for the next month. So yeah, probably the easiest one out of here, I would say, would be doing a 200-meter baseline, although our technology baseline really doesn't matter. So here are the results for that. This is 1-month measurements. The light blue values are absolute 1-second interval values. So you could call this the absolute maximum error that we've seen over a month. So it goes down to almost minus 50, 500 picoseconds, and just over 500 picoseconds on the other end. Then if you average this data over 2 hours, we stay really close to what's it, 250, 300 picoseconds over time. So we were quite happy with the results. There's some sort of a bump in here, but never mind the scale. You do see it. We have not found out what it is. It could be temperature changes in the end, but at this level, it could be the optical link. It could be our GNSS DO. It's really hard to say, but we claim to be within a nanosecond. I think we achieved that pretty easily. Then we also plotted the ADEF of this time transfer as well between the two. ADEF goes down nicely again to 10 to the minus 13 at 1,000 seconds, 10 to the minus 14 at 10,000 and down. We can plot more than this on the data than we have here. Also, the TDEF is plotted here as well, which is exactly how we expected it. Now, you'd say this is probably the easy one because it's close. Doesn't really matter again. After all the data was still sent over the air, we still use GNSS as a reference. But then we went to the DTAC measurements, which is 300 kilometers apart. We unfortunately had a couple of data outages on the 1 month data that we were collecting. So we didn't get much more than 5-6 days in a row. Some issues with the tick and recording and storing it off and then uploading it. Still, if you look at this trend, I cannot believe that in the biggest gap, it will go up and down much more than what you see here. So it's very similar performance to what we've seen on a short baseline. Actually, it's even a bit better. So we're very happy with this as well. Also drawn a modified ADEF on this and a TDEF, looking very similar and getting to the same levels as the short baseline. So that was a good result. Then lastly, the long 700 kilometer baseline, which was really interesting because we started measuring here the first week and we're like, oh crap, it's going down. But we are measuring here UTC PTB from the GNSS DO against UTC SP in a remote location at Rice. So we cannot compare it one-on-one because they differ from each other. So what we did afterwards is we processed all the two-way satellite time and frequency data as well, which is the red line here. And we waited for circular T, so the official BIPM data to come out, and overlaid that as well. Now, I'll tell you there's a bit of an offset here. The 2-hour average data to the BIPM data is about 500 picoseconds, more than what we would like. We like it better the way we see it here. But I don't think you can get this with any GNSS DO today without having augmentation. And honestly, it's performing quite similar to two-way satellite time and frequency transfer as well, which is a technology that is multiple times more expensive than what we use. Also on this, we plotted the ADEF as well. Very similar performance, maybe a little worse, but looks quite similar to the others, as well as the TDEF. So this basically gave us the proof that what we're doing is verified, it works, and anybody can get this, basically. All right. Going really fast. Are there any questions in the intermediate? I don't have too many slides left anyways, but if not,
just
yeah.
quickly roll. Like I think you might have it already further down the slides, like the update.
This is the update.
Okay, this is the update. Okay.
Yeah, we would not be able to reference against a local UTC realization before.
I see. Okay.
Yeah.
All right.
And the update is also that you now can buy hardware. You can order it online, and you can actually use it today.
Yeah, wonderful. Yeah. Thanks to the guys from SparkFun. Yeah.
Yes. So yeah, what can you do with this? That we're running in a bit of an issue sometimes that okay, we think about applications, but many of these applications people either have shelved, and we found a couple of those because to get high accuracy time synchronization, sub-nanosecond time synchronization, they needed fiber optic links, commercially not viable sometimes. Sometimes it's just the locations are so remote they cannot use it. So What you can use it for, of course, it's high accuracy time transfer and a reference anywhere in the world, without any limitations on where you are, without any limitations of having dark fiber or any fiber available. So that is, I think, a big advantage at a relatively low price point. Also, if you have a lab and you're doing testing on, and you need a stable frequency reference, you can use this. You don't need to buy a passive hydrogen maser to check a cesium, for example. You can use this to check your cesium. You cannot check your passive hydrogen maser with this, although if you wait long enough and average long enough, you will find where this will take over. And we actually also have interest in optical clock companies that are looking to use this with long enough averaging to actually check out how good their clocks are doing. Of course, those clocks will do the short term, and the short term can then run into 10,000 or 100,000 seconds tau. But after that, we can still check how they're doing. Then it can be used for calibration of long fiber optic links. We have a project that we're gonna try doing this hopefully soon, hopefully this year. Basically requires receive from both ends on the links. You can monitor those links as well, by the way. You can replace them totally. I mean, I'll leave that up to anybody that wants to use this technology. Now, also traceability to UTCk in real time. I think I think it could be useful. Of course, today there are no regulations out there that say that you have to be traceable to within a nanosecond. But whatever you would use this for in a product, you could also, in the same time, use it to prove you're traceable to a UTC NIST or a UTC PTB. We will be adding other references in the future as they come by and people request them. And again, it's a commercially contracted service to these organizations. That does not mean that they will have 100% uptime, but you can still use it very dependently. We always had and still have historical timescale traceability to UTC. Basically, we track our timescale against UTC whenever UTC is published, and we always know the offset historically, so that's always there. One thing that we kind of add to this right now, I think, is monitoring and also characterization of cesium, hydrogen maser, optical clock stability, which only requires to feed the GNSS DO or even a dev kit with the clock, and then you can actually, in time, as I mentioned, check how your clock is doing, but also how it performs. Now, I presented last time around that we've partnered integrating this in the Septentrio MOSIC T. That's still the case. It's also, you can get this technology in the Meinberg. It will not perform to sub-nanosecond. A couple of new additions to that is because we only have a service, it's kind of handy to have hardware. We also partner with Viavi Solutions since last time. Basically, these boxes come in out of the Jackson Labs, if you're familiar with them, a business that Viavi bought a couple of years ago. This will give you to a couple of nanosecond solutions, still not to the full high accuracy. So I'd say semi-high accuracy. It will give you NMA as well, by the way. But now I think the SparkFun GNSS DO, I think that's really a winner if you want to achieve the highest accuracy possible, small form factor, low price, and get you what you need to get going on this technology. So yeah, and that's already I think it's like 33 minutes, not too bad. A couple of thanks to SparkFun, PTB, Rise, Deutsche Telekom, and my colleague at Fugro for preparing all this data and working on this. So if there are any questions, yeah, let me know.
Wonderful. Thank you very much, Roel. So yeah, let's open the floor for questions. Make sure you unmute your microphone. Maybe I can start with a, like, what do you call a icebreaker question? Like, how is, can you show us a little bit in terms of a pricing?
There's always a wrench thrown in that you didn't expect. It's very rare for a design to.
Okay, that one is, I think.
Okay, that was accidentally.
That was a hot mic. Okay, yeah, so can you share with us, let's say, some kind of like, let's say, pricing or like how it goes like with the license you need?
Yeah, for a licensing, high accuracy license is $1,000 a month or 10,000 a year. So that's basically it.
And then is there a cheaper thing, let's say for like hobbyist or something, or like there's no
Yeah,
such?
well, people that are here that also are familiar with the Time Nuts mailing list, there are quite a lot of hobbyists on there.
Yes.
If you want this at home, so you choose to buy GNSS DO or dev kit, we can give discounted pricing on that. I got my email address on the first page. Just reach out
Okay.
if you're interested in that, and
That'll be case by
I
case.
can hook you up on that. Yeah.
All right.
It's heavily discounted. I'm not gonna say it's for free still,
Yeah, yeah.
but much down from the $10,000.
All right. Anyone else? Steve.
Roel, I have a question. When you do the calibration, what is the time base that goes into the tick?
Yeah, so let me go back. Here.
Yeah.
Yeah, so what we take into the tick is the UTC realization of PTB. That's the reference.
Okay.
And then we feed the GNSS DOs to check against that.
Okay. So you're using the UTC PTB as your reference there.
Yes, and you can do the
Okay.
exact same thing at NIST. You would obviously have to be at NIST to do that, or have a local NIST transfer that is within a nanosecond, but those don't really exist today. So yeah, I think where we're gonna go in the future is probably work together with either NIST or PTB, or we do it ourselves, that we will get a couple of GNSS DOs calibrated and use them as a golden standard to ship around if people want to do an on-site calibration. That's an option as well, of course. Otherwise, you can send one into NIST, and NIST will calibrate it to their time realization. They can do that. They do that on GNSS receivers already today, and they can do it also on this.
Okay. Thank you.
Roel, like just from your knowledge, do you know any, are you aware of any product that uses, let's say, for example, a cesium clock that like gets disciplined with your service?
Not yet. The thing is, a cesium, I don't think a cesium will probably ever be disciplined with this. It could be. What you can do though with the GNSS DO, the one that's on the market today, is you can also feed it with an external clock. And you can make your own GNSS DO based on the
Yeah,
external.
no, of course, yeah. I thought it's like there's no vendor that already is working with you on something like that. There's nothing like that.
There are vendors, not cesium clocks, but other clocks that are interested
I see.
in integrating this for long-term stability on their clock solutions. Yes.
I see. All right.
And then basically what you're getting is what I showed before. Let's say you take an optical clock, an iodine clock or whatever. Basically this line, which is now a side time MEMS, will go down all the way here, probably. And it will run the optical clock in the short term again, but it's not really short anymore until it hits the level where that optical clock starts to drift, and then AtomiChron kicks in.
Wow. Yeah.
Which is, I mean, still, if you want to run something for a long time, you still would want that in the end, I guess. If you want at least reference to UTC or to another location. Yeah, and we're talking to several parties about this.
That's great. Anyone else?
Can I ask a question, Ahmed?
Go ahead, Hasham, go ahead.
Yeah.
So you mentioned that you attended a conference in Mexico.
Yes.
Excellent. Do you have the proceedings of that conference?
The proceedings are not done yet. What I do have is the procer we presented, and I can send that to you. But the paper is due by the end of the month, and the proceedings will follow after that. So,
Good. Yeah, please send Ahmed the roster, yes, the poster or whatever.
Yes,
Yeah.
That was EFTF, right?
It was it's a combined IEEE IFCS and EFTF conference.
Oh yeah.
Yeah.
In Mexico this year, that's
Yeah, every other year it's combined IFCS, EFTF. The other year it's just EFTF. So next year, European Frequency and Time Forum will be in Europe again, and IFCS will be in Tampa, Florida.
What about in Mexico?
Yeah, in
The,
Mexico. Yeah, go ahead. Sorry.
Which city?
Oh, it was in Querétaro.
Okay. So anyway, when the proceedings are available, please let us know.
Yeah, again, the paper will be ready by the end of the month, and then I can send the paper already then.
Yeah, send it to Ahmed. Send it to Ahmed, and he will
Okay,
distribute.
I will forward. I mean, we are all on that WhatsApp group for
Oh yeah, I can
common
put it
appliances, so he puts it there.
I can
Exactly.
put it
Yes,
there, no
yes.
problem.
Yeah.
That will be excellent. Yes.
All right, no problem.
All right. Any more questions from the audience? Products, ideas, comments.
Yeah, products, please. Well, one thing I want to mention is that we have a hard time. A lot of people have a hard time actually believing what we claim. So I mean, I think teaming up with a PTB and a Deutsche Telekom and a RISE already helps a lot. But again, the GNSS DO, you can buy it for $2,500. If nobody wants to spend money on the service yet, I offer everybody a 1 month free trial. If you're still not convinced after that, then I don't know what to do anymore. So I can show you one more thing, maybe nice to see for some people. So what we've been doing for a while already is just track a bunch of different clocks. And these are mostly either UTC realizations or hydrogen mesas directly measured with Polex 5TR GNSS receivers. Then the observations are streamed to us. We real-time process them and display them on Grafana. So let me take the last 24 hours, for example, of data. What you can see here on the left is it's 600 picoseconds accuracy. I'm sorry, scale. 600 picoseconds from 0 to the top, and we measure several clocks here. So it's a Fugro clock, our clock. Then there's a clock from TimeTag, which is the party being used for NMI intercomparison, two-way satellite time and frequency transfer, but they also have their own clock realization back in Munich. I'm sorry, Stuttgart. Then we track the clock in Brussels of the observatory. In Brussels, we have 2 ESOC clocks. We have access to INRIM in Italy, JV in Norway, PTB in Germany, ROAC in Spain, and SP in Sweden. And then we also have NIST, but I'm not showing it here because right now, for some reason, the NIST clock is not connected to a reference, and it will show you a nice sawtooth. We will work on fixing that for sure. This is, by the way, a different clock than what we use for the UTCk service, so no worry about that. And basically what you can see here, these are very stable clocks over 24 hours. There are ranges of 190 picoseconds, 310 picoseconds. Some of them deviate at times. That happens. We actually see some timescales fail, not being steered well in these plots. But it just gives you an idea of how accurate you can measure clocks. I mean, try measuring a passive hydrogen maser accuracy over time with anything else, you'll never get this.
Just to clarify, Roel, how is this measurement done? This is measuring every clock versus the average of all, or like
no, basically we subtract all the offsets here. So they're all
the offset is from what versus what?
Yeah, well, that's the problem. These measurements are not calibrated. So we just take the stability into play here.
So that's a variance only.
Yes. What we can also do, we can do time transfer between clocks as well. I can show you that as well.
So basically, the beginning of your measurement is considered 0, and then you just look how you wander around.
Yeah, well, actually, these are offset like hundreds of nanoseconds, but we subtract the minimum in the plot.
Okay, I see.
But we can also measure them against each other. We can do time transfer, for example, TimeTag in Stuttgart and P2P in Braunschweig. and these might be calibrated. I'm not 100% sure, but we can do time transfer over time. And the good thing about time transfer is, if you do time transfer, our time scale doesn't matter anymore. It falls out of the equation.
Yes.
So we can just select, let's say I want Italy and PTB, they will be compared. And again, we don't have the full calibration values of all of them, so we cannot say it's just actually minus 400 nanoseconds between them. But if that will be calibrated and you use it in a product, that is no problem. You can do that.
Mhm.
And one last one I wanted to show, which I think is kind of nice, is that I show you on the bottom, I show the PTB clock again, because again, it's one of the most stable realizations in the world. And I'm also showing you, it's called Roel Demo, which is a GNSS DO right here on my desk right now. And this is 12 hours of data. And the stability is just very, very nice. Let's put it that way. All right. Any other questions?
Right, hearing none. Then
Well,
probably we can give the rest of the time back to everyone, and basically we'll see everyone in 2 weeks by a call from Mark Weiss. But time transfer this time, right? Time transfer and ensembles across moving platforms. All right, and thanks again, Roel, for your informative presentation. And,
yeah, no problem.
looking forward to see more applications taking advantage of it.
Yeah, that would be great.
Yes.
I'll
All
send
right.
you the slides as well, Amat.
Thank you. Thank you.
All right.
Bye, everyone.
Thank you. Goodbye.